All right, so we're going to walk through a visual of the ear. The outer ear, the middle ear, and the inner ear, and the major structures that you need to be familiar with. So we're going to start with the outer ear. Of course, the ear that everybody's familiar with is the part that sits on the outside of your head, and the official term for that is the pinna. It's primarily made of cartilage, although the lobe at the bottom doesn't have any cartilage. And it's just attached to the outside of our skull with some tendons. It does have a few muscles in there, but they're vestigial, they're not functional, they don't serve any main purpose. All right, so we have your skin and some muscle, and then in here we're going to start to see the actual bones of the skull. Okay, this is going to be part of your skull here with that spongy bone. Just like that. Now, the pinna helps to protect all of the very delicate structures within the middle and inner ear. It has a little bit of a role in gathering sound and helping to funnel it into the ear. All right, then we have our external auditory meatus, or ear canal, okay? And it ends with the tympanic membrane, and that's where the middle ear starts, is at that tympanic membrane. Now, the external auditory meatus is an S-shaped tube. It's not perfectly at a right angle to the rest of our body. It does help to protect the intricate parts of the middle ear. It helps to filter out debris, kind of like our nose does. It has hair and little cilia cells that help to kind of brush all of that dirt out. But what we really care about with this external auditory meatus is the fact that it basically acts as an acoustic resonator. So just like the vocal tract, it is this irregularly shaped air-filled tube. Also like the vocal tract, it's a quarter wave resonator, meaning that it has one end closed, where the tympanic membrane is, and one end open. And we know that acoustic resonators are able to increase the amplitude and amplify certain sounds. So our external auditory meatus actually has its own resonant frequency. Okay, and its resonant frequency is around 3,500 hertz. That's the rate that air likes to vibrate within it. But because it's irregularly shaped, it has a pretty wide bandwidth. And so what we see is it's able to resonate or amplify high frequency sounds from about 2,000 to about 5,000 hertz. Okay, now that's really important because our ear in total has the ability to pick up sounds from 20 to 20,000 hertz, from very low to very high sounds. But this is the range that we see that a lot of speech occurs in, particularly high frequency sounds in speech. So speech sounds are going to occur from about 100 to about 4,000 hertz. That's the range of speech for children and adults. So you can see here in this bandwidth, it specifically is able to amplify high frequency sounds. And these are going to be sounds like s and sh in English. What's really cool, and your book talks about this, is that if you didn't have this external ear, and if you didn't have this acoustic resonator of the ear canal, then our bodies really couldn't pick up on these high frequency speech sounds. And so you can see our body is so amazingly created to communicate, right? It's designed from our vocal tract to be able to communicate verbally, but then even from our ears, it's designed to pick up specifically on speech sounds and highlight those higher frequency sounds. All right, so now let's get to the middle ear. So it starts right here at the tympanic membrane. And the tympanic membrane is a tough little cone-shaped membrane, and it separates the outer ear from the middle ear. All right, let's draw this middle ear space. So it's all surrounded by this bony area of your skull. And it just forms this little empty air-filled space. And it's pretty tiny. Think about like a medicine dropper. The volume of air in your middle ear is only about 2 milliliters, so it's pretty tiny. On this left border, we have our tympanic membrane. And then over here to the right border, we have the entrance to the inner ear, which is primarily the cochlea. Okay, and then down here at the bottom, you see we have this kind of empty tube. That right there is our eustachian tube. So one end of it starts here in the middle ear, and this goes all the way down to our nasopharynx. And it lets out there. So we can't see the exit to the eustachian tube because we can't see the nasopharynx, but that's where it lets out at. And the eustachian tube is really helpful because this is a pretty closed container, right? It's all enclosed in this bony structure of the skull. So the nasopharynx allows a way for air to enter and exit so that pressure can be equalized. It's also really helpful when you have a fluid in your ear or some kind of cold because it allows mucus to drain out into the nasopharynx. So let's go back to this tympanic membrane. So your tympanic membrane is actually a 3-layered structure. It has a lateral layer that faces the outside of the ear. It has a fibrous layer, which is in the middle. And it has a medial layer, which is on the side of the middle ear. Okay, now if we were to look in the ear with a tool called an otoscope, which is a way to visualize the tympanic membrane, we would see something that looks like this. In a healthy person, the tympanic membrane should be a light pink color. Right in the middle, there's a structure called the umbo, and it's where the tympanic membrane is pulled slightly into the middle ear space. So it's concave into that middle ear space. Now this fibrous layer is full of these tough fibers, and it helps give the tympanic membrane tension. And all of these tough fibers, if we were to look at this like a pie piece, make up this bottom 3/4 of the pie. And there's quite a lot of that fibrous layer in this bottom 3/4. We call that bottom 3/4 of the tympanic membrane the pars tensa because it's tense, it's fibrous. This top portion here has a lot less of those fibrous layer, so we call it the pars flaccida, right? And think about the word flaccid. It's floppy, it's weak, it's flexible, okay? All right, the other structure you should be aware of is that whenever we put an otoscope in somebody's ear, we have a little flashlight on the end, and that's how we're seeing what's going on here. And in a healthy tympanic membrane, that tissue should be reflective. And so you'll often see a structure called the cone of light. And all that is this bright white spot where the flashlight is reflecting off of that healthy tissue. If you don't have that reflection, that might be a sign that the eardrum or the tympanic membrane is not as healthy as it should be. If you have something like an ear infection, you're probably not going to have that cone of light. This tissue will be red and inflamed. So those are just kind of signs that an audiologist or an ENT is going to look for to make sure that that tympanic membrane is healthy. So the umbo is where the tympanic membrane is pulled backwards a little bit into the middle ear. And that's because there is another structure here that's embedded within those layers of the tympanic membrane. And that's going to be one of your ossicles. You have 3 teeny tiny bones in your middle ear called ossicles, and they're the smallest bones in your body. You have a malleus, an incus, and a stapes. And one of your best tools to study, particularly with anatomy, is to search on Google. You go on Google and you're going to search malleus etymology. Etymology is where words come from, their Latin and Greek roots, and it really helps you to learn these new and unusual words. So if you look up the malleus etymology, It literally is Latin for hammer. Incus etymology is going to be Latin for an anvil. And the etymology for stapes is going to be what do you call it? Not a saddle. I can't say the word. A stirrup. And what's really nice is that each of these structures really resembles each of these items, which makes it easier to remember. So like I said, the malleus is this first bone in the ossicular chain, and it's actually embedded within this tympanic membrane. So the umbo is where it embeds, but then the handle of the malleus, also known as the manubrium of the malleus, that manubrium is also embedded up here in the pars flaccida. All right, so then we have this point of articulation between the malleus and the next bone called the incus. And the incus, just like it sounds, looks a little bit like an anvil where it has a kind of a big top and a little bottom. And then it articulates to the last bone, the stapes. And the stapes is the last part in that ossicular chain, and it lines up to a structure called the oval window. And the oval window is the dividing line between the middle ear and the inner ear. Okay, so our inner ear consists of our cochlea, and the cochlea has semicircular canals on top. So these semicircular canals are responsible for balance, but we're not going to get into that because we're focused on the part of the cochlea that's responsible for hearing. And that is this kind of snail-shaped structure here. And then coming off of the cochlea, you're going to have cranial nerve, number 8, the vestibulocochlear nerve. Okay? So back to the middle ear. One of the problems we have when we're trying to transduce energy from these pressure waves of sound and getting it all the way here to this inner ear is that all the way up to the tympanic membrane, that pressure wave is traveling through air. Then it hits the tympanic membrane, and the tympanic membrane acts like the diaphragm in a microphone, to where it's going to start vibrating at the same rate that those pressure waves hit it, and it's going to travel in and out. So as those tympanic membrane starts to vibrate in and out, it's going to start moving the ossicular chain because that malleus is embedded in the tissue. And so it's going to move that ossicular chain and start bumping into that oval window. So we've gone from pressure waves through air, okay, to mechanical energy, the movement of these physical objects, also in air, to the cochlea, which is going to be a fluid-filled structure. So if you remember when we talked about sound, sound can travel through air and liquid and solids, but whenever sound has to go through two different mediums, it loses most of its energy or it's reflected off. And if you think about density, air is less dense than liquid. So when a sound wave travels through air and it hits this new medium of a fluid, the majority of the sound wave is just reflected off. It's like hitting a solid wall. And that's not going to be very conducive for an efficient energy transducer. So part of the middle ear's job is to do something, is to overcome what we call impedance mismatch. And all that means is that it's able to overcome this barrier from air, mechanical energy moving through air, to moving through a liquid. So basically what it has to do is it has to increase the energy of the signal so that there's enough energy that by the time it gets to this liquid, it will start to transfer energy over to the fluid-filled cochlea. And it's, imagine like you're in a swimming pool, right? If you're underneath the water and you try to speak to somebody above the water, they're not going to be able to understand you because there's not an efficient energy transfer. It gets a little bit better if you yell which is an increase in that amplitude, right? That energy. So the first way that the middle ear does that is through a change in surface area. All right, so force is just the amount, a force applied over a surface area produces pressure, right? So if I have this much force on a large surface area, that pressure is going to be spread out or dispersed. But if I put the same amount of force over a small surface area, then the pressure is going to be much, much higher because it's all getting forced into that small surface area. And so the first way that the middle ear increases that pressure to get into the inner ear is going to be through decrease in surface area. So if this is the size of the tympanic membrane and this is the size of the oval window, we're getting a much smaller surface area for that same amount of energy and pressure to get to. The other way that it helps to overcome that barrier is through levers. So if you remember in other science classes and talking about simple machines, a lever is a way to increase the energy output of something. So for example, if I needed to pick up a really heavy rock, I would have to use quite a lot of force to do that by myself. But if I use a lever system to pick up that really heavy weight, then I can produce less pressure, less energy on this side of the lever to get a much larger amount of energy on this side. So where each of these bones articulate, those act as a lever or a hinge system. And it increases the energy and the pressure to the cochlea by about 10 decibels. So those two together really increase the strength of that sound wave to overcome that impedance mismatch. But this is what's really crazy, is that even with your body working to overcome that, only about half of the sound that enters your external ear makes it to your internal ear. That's how much is lost through this transduction process. All right, the last thing I want to show you is two muscles within the middle ear. Okay, we're going to get into the cochlea next week when we lecture on that in greater detail. So you have two different muscles. One is going to be the stapedius muscle, and it connects from the stapes to the posterior wall of the middle ear. And it's really cool because it's responsible for something called the acoustic reflex. What happens is when you have very, very high energy, very, very loud pressure waves entering the ear, those super loud pressure waves can actually damage cells within the cochlea, causing hearing loss. And so the acoustic reflex is helps to protect the inner ear from very, very high intensity, high pressure sound waves. So when a very, very loud sound enters the ear, the stapedius muscle will tense and it stiffens the ossicular chain. Whenever these levers are not working quite as well because that chain is stiffened or pulled tight, then less energy makes it to the oval window. So it's just a really cool way that our body has this protective mechanism against really loud sounds. The other muscle in the middle ear is going to be the tensor tympani muscle. And it runs from the malleus, and it runs over here parallel to the eustachian tube. And whenever that muscle tenses, of course, it pulls the malleus medially, and it helps to actually tense up that tympanic membrane. All right, next week we're going to get into the really complex anatomy of the cochlea and the inner ear, and how that final step in the transduction process, how we go from pressure waves to mechanical energy through the movement of these bones, to fluid energy, to an electrical transmission to the brain. The only other thing I want to point out that I think we spoke about in class is this eustachian tube. So we talked about how the eustachian tube is responsible for keeping air pressure regulated in the middle ear, but it's also responsible for draining out fluid. And this is why little kids get so many ear infections, is because if we're looking at an adult, and here's their ears. In an adult, eustachian tubes run downward, okay, towards the nasopharynx. And so if you get a really bad cold and there's mucus backing up into those eustachian tubes, gravity is helping to pull that mucus downward back into the nasopharynx. And fluid isn't allowed to build up in the middle ear. But in babies and toddlers, all of their structures are much smaller, much closer together. And so their eustachian tubes run perpendicular to the rest of their body. And this means that gravity isn't able to effectively drain out that fluid. So oftentimes, little kids, if they get a cold, that mucus will backtrack up the eustachian tube through the nasopharynx and just sit in this middle ear space. And if it sits there long enough, it can get infected with bacteria. It can cause this tympanic membrane to bulge out, which is really painful. And the other thing is that, of course, these bones, if they're stuck in this sticky, gunky fluid, they're not going to be able to move as easily or articulate the bones against each other very easily. So it can actually cause a transient mild hearing loss, which is a concern for our babies and toddlers.